everyone. I'm going to make a start. Would somebody mind just getting the door, please? Okay, guys, can I make a start then, please? Somebody, sorry. I'm sort of tethered now, so could somebody grab the door for me, please? Okay, so we're going to... last time we met, we looked at the preliminaries chapter, which is the chapter 1 in the notes. That sort of stuff which you should have already covered before in previous study in mathematics, but you also need for this unit. So hence, I've called it preliminaries. It's kind of stuff which sort of revision for you, stuff you've done previously. Okay, so today's session should be all brand new stuff to you. And what we're going to be looking at is what's called explicit Runge-Kutta methods. Okay, these are methods which you've already seen. Okay, the Runge-Kutta methods which you've used up until now are explicit Runge-Kutta methods. Okay, there are 2 types, and the other type we'll be looking at in 2 weeks' time. Okay, so this is explicit Runge-Kutta methods, and this begins at page 11 on chapter 2 in your notes. Okay, so what we're going to be looking at today is the derivation of these methods. You've used them. We used them last time. We used the second-order Runge-Kutta method. Last year, you had experience using 4th-order methods. What we're going to be looking at today is actually where they come from, their derivation. Okay. When I say this session, I mean this first hour and the second hour as well. It's a 2-hour lecture, which I'll split in, obviously over the 2 hours. Okay, so by the end of today, what we're going to be looking at is writing Runge-Kutta methods using what's called a butcher tableau. This is just a method which it makes it easy to write down Runge-Kutta methods. It's kind of like a shorthand, and we'll be looking at that. We'll be looking at derivation of 2nd, 3rd, and 4th order explicit Runge-Kutta methods. Okay, and finally, we'll be looking at solving initial value problems using these explicit Runge-Kutta methods. I may have to change this a bit because I've just been on this computer and it requires a password for me to use MATLAB, which I was hoping to show you all the demonstrations using MATLAB. Unfortunately, it hasn't been set up properly on this computer, so I might have to change some things for today. So my apologies for that. Okay, so I'm just going to recap from last time we met, just so it's fresh in your mind. Okay, so this is all the stuff we looked at last time. Definition of an ODE, kind of fundamental for this unit. Okay, what is an ODE? Well, quite simply, it's an equation that contains a function of one independent variable. And in my notes, I've always used t as the independent variable. I think Leader uses x, but it doesn't matter. So t is the independent variable. Y is some function of t. Okay, and then we could have derivatives of y. Okay, so it's an ODE which is written as an independent variable, t, a function of t, and the derivatives of this function. Okay, so in this case, it's an nth order ODE. The order of an ODE is the highest order of the derivatives that define it. Okay, all the methods we look at to solve ordinary differential equations solve 1st order ODEs. So if we got a higher order ODE, we just convert it into a system of 1st order ODEs. Okay, so the order of an ODE is the highest order of the derivatives that define it. A linear ODE is one where it can be written as a linear combination of the derivatives. Okay. You'll be looking at nonlinear ODEs if you do dynamical systems and chaos. Okay, this brings us on to an initial value problem. This is kind of the main type of problem that we solve using ODEs. Okay, initial value problem is where we know what the value of the function y is at the initial value of t. Okay, so if we have the 1st order ODE, here we've got 1st order because it's a 1st order derivative, some function of t and y. If we know the value of y at the initial value of t, so a is the initial value of t, if we know what that is, that's some value, This is called an initial value problem. Okay. If we had a higher order ODE, we have to know, in order to initial value problem to be defined, we have to know the initial value of the derivative. So if this is a second order ODE, we'd help, as well as knowing y at the initial value, we'd also have to know y dash at the initial value. Okay, so that's what an IVP is. It's an initial value problem. We know what the initial value of y is. We have a unique solution for IVPs if that function f of ty, if that is continuous in the region containing a and y0. All of the IVPs which we'll be looking at have a unique solution. So you don't have to worry too much about that. Okay, one thing we've been looking at a lot of today is this Taylor series. Now, hopefully by now it's sort of ingrained in your brain and you could write out Taylor series to your heart's content. Okay, this is something you really need to sort of memorize. Okay, this is Taylor series. We looked at its derivation last time. Okay, so it's essentially infinite series. So the function or the value of the function f at t plus h is a series, and the nth term is h to the power n over n factorial multiplied by the nth derivative of that function at t. Okay, the more terms we have, or the higher the value of n which we sum to, the more accurate our series approximation. Okay, so that's the Taylor series. Of course, we've got to stop somewhere. We can't keep summing for infinite number of terms. It will take forever. We've got to call it a day sometimes. So what we tend to do is we truncate the Taylor series. Okay, so we just sum the first few terms, and we refer to that as an order n. Okay, so the term which we stop on, let's say we stopped on the second term, or the n equals 2 term, that's a second order Taylor series expansion. Okay, so that's what we mean by truncating. We call it a day. We eventually stop summing all those terms. The truncation error, because if we stop at a certain number of terms, we're not getting the exact value of f of t plus h. So this is what we call a local truncation error. Okay, so there's some error which is attributed to ignoring those higher order terms. And this is expressed as big O, so big O notation, h to some value n. Okay, just notice here there's a little typo. That should be n plus 1 there, that h4. I don't know what it says in your notes, but if we stop at the nth, when nth order, the power of the h should be n plus 1. What does this mean? Well, order h to the n means that as h, and just remember that h is the step length. Okay, so h is some short step away from t. So as that step length tends to 0, the truncation error also tends to 0, proportional to h to the n. So in other words, higher the value of n, the faster the truncation error tends to 0, and therefore the more accurate our approximation. Okay, and that's called big O notation. We'll be using a similar notation in term 2 to mean something totally different. Okay, so just to confuse you, there'll be a similar notation, but I'll explain that when we get to term 2. Okay, so last time we also looked at the bivariate Taylor series. Okay, so Taylor series of one variable, t, is there. Okay, we could also have Taylor series of 2 variables. And I've just introduced y. So we've got f is a function of t and y. Okay, and this is the total derivative. And I derived this last week, and it's in the preliminary section. Okay, so this is, if you want the nth derivative of fty, we use this operation notation there. Okay, so these are, notice the difference between the partial derivatives and the standard, the ordinary derivatives. Okay, that's a total derivative, and using that, we can derive a bivariate, so a 2 variate Taylor series. Okay, quite similar to the one variable, so we've got 1 over n factorial. We have this total derivative, okay, to the power n, and that's applied to our function f. Okay, so for example, if I was to look at the first order bivariate Taylor series, okay, n is 0, so we've got 1 over 1. Anything to the power 0 is 1, so therefore it's f of ty. Okay, when n is 1, we have 1 over 1. This is to the power 1, so we simply have h times the partial derivative of f with respect to t plus k multiplied by the partial derivative of f with respect to y. And there's a truncation error. So the truncation error is in terms of h and k because they're 2 step lengths. So my step length for the t variable is h, and my step length for the y variable is k. Okay, second order, slightly trickier. So second order, okay, we have first 3 terms are the same as the first 3 terms of the first order. But now when n is 2, we have 1/2. Okay, and we have a, expand out this bracket to the power 2. So we have h squared times the double partial derivative of f with respect to t, plus 1/2 times 2hk. So 1/2 times 2hk is just hk times fty. So we've got a mixed partial derivative of f. And finally, excuse me, 1/2 times k squared times the double partial derivative of f with respect to y. Okay, so you can see I could do a third order bivariate Taylor series. I just add the n equals 3 term onto the end of this. Okay, we'll be using that in the derivation of our Runge-Kutta methods today. Okay, so it does take a bit of getting used to, okay, where's that term come from? But if you read the preliminary section again, make sure you're very familiar with the total derivative and the bivariate Taylor series. Okay, so that was what we looked at last time. What we're going to look at today is the derivation of Runge-Kutta method. And a Runge-Kutta method is an example of a single-step method. There are 2 main types of ODE solvers. We've got single-step and we've got multi-step. In Nida's half of this unit, she'll be using multi-step methods. We'll be just concentrating on, in this half of the unit, on single-step methods. Now, a multi-step method is a method that requires previous values of y in order to advance a solution. Okay, so for example, second order Adams-Moulton, okay, to advance a solution to the next value of whatever t is, so yn plus h is the next solution, yn is the current solution, and this is multiplied by something times the f of tn yn, so that's the tn yn and the current values of t and y, minus, and then we've got the previous values, tn minus 1 and yn minus 1. So we have to have values of y at 2 different sort of time steps, 2 different levels. So therefore, this is called a multi-step method. Okay, so multi-step methods tend to, okay, we remember what the values of y were in all the previous steps, and we use them to advance the solution of y. Single-step methods only require the current values. Okay, so in order to advance the solution, a single-step method just requires the current values of t and y. Okay, so the simplest single-step method is the Euler method. Okay, so the next value of y is the current value of y plus some function of the current value of y. Okay, Runge-Kutta methods fall into this single-step method category. Okay, we only need the current values of y in order to calculate the next value. Which one's best? Multi-step methods use less function evaluations, okay, but require more memory. Okay, we have to remember what all the previous values of y was in order to calculate the next value. Single-step methods Okay, use more function evaluations, but we don't have to store as many things in the memory. The best type of method will depend upon the problem. There's a little bit of a discussion what the best type of method is. Okay, Leader thinks multi-step methods are better. I tend to think these are better, but it depends on what the problem is. But don't tell Leader that, by the way. So that's what we're going to be looking at. We're going to be looking at single-step methods. All of the methods we look at to solve can only solve first-order ODEs. What if we have a higher-order ODE? Well, as we looked at last time, if we let y1 equal y, y2 is the first derivative, y3 is the second derivative, etc., we can write our nth order ODE as n first order ODEs. Okay, so we have a system of n first order ODEs. We apply our solvers to each of these. Okay, because these are just first order and we can solve them at the same time. Okay, so if we write the left-hand side of all of these, the first order derivatives on the left, we write this as some vector of the y1s, y2, etc. The right-hand side of all of these, okay, we write as big F, which is our f of ty, but where y, that's a vector there. If you notice, it's in bold. Okay, so for example, the Euler method is simply the vector y plus h step length times big F, which this also happens to be a vector, but it's not written as a vector because it's a function of a vector. We looked at that last week, and when we look at boundary value problems, we'll be looking at that again. Right, so this brings me on to explicit Runge-Kutta methods. Okay, so we have a first order ODE. So y dash equals some function of t and y. Okay, this is the general form. Okay, so the next value of y is equal to the current value of y plus a sum of I, let's say, we have a sum of s by stages. Okay, so current value of y plus b1 times k1. Now, b1 is going to be a coefficient. That's just a value. So is k1. Okay, k1, k2, k3, etc. These are known as stages. Okay, these are intermediate stages. If you think about it, they replace the multi-step stages. So instead of having multiple previous values of y, what we do from the current value of y to the next is we calculate intermediate stages. Okay, so current value of y plus b1 times k1 plus b2 times k2 plus b3 times k3, etc., etc. There are s stages. Okay, so if I have s stages, this is the what the stages are. The first stage is always the step length times f of ty. So if we're only to sum to s equals 1, we have the Euler method. So the first order Runge-Kutta method is exactly the same as the Euler method. Okay, if s is 2, we have to include this one here, and this introduces this c2 value. Okay. C2 will be some number between 0 and 1. Okay, so it will be t plus some fraction of our step length. So it's not quite the full step length, but it's some fraction of the step length. So remember, we have this function f of ty. For k2, we replace t by t plus c2 times h, and we replace y by y plus a21 times k1. Now, a21 is an element of a matrix, and k1 happens to be whatever that previous stage was. Okay, there's a pattern there. Notice the t plus c2, t plus c3, t plus c4, etc. And the s stage is t plus c, s, h. So your c's are what we multiply h by. The a's, which are elements of a matrix, are what we multiply the previous stages of k by. Okay, so there is a pattern there. Okay, so that's the general form of an explicit Runge-Kutta method. this is usually commonly expressed in what we call a butcher tableau. Now, a butcher tableau is simply like a table. And it's a table of this form. Okay. It's kind of like there's 4 quadrants to the butcher tableau. The top left quadrant lists our values of C. Okay. And this is usually in a column vector. So I'm going to flick between this slide and the previous slide as I explain this. Okay, so if I go back to the previous slide, our values of C are what we multiply the H by and then add it to T. Okay, so we'll have S values of C. So if we have S stages, we'll have S values of C. Notice the C1 value is 0 here. Okay. So our C values, and as you can see by this one here, it's like a column vector going down in this first quadrant. Okay, in the bottom right quadrant, I have the B values. Okay, so these B values are what we multiplied by the K values. Okay, so going back to the previous, we update the value of Y by adding B1 times the first stage value plus B2 times the second stage value. So our B's are what we add on, or what we multiply the stage values and add them on to Y. Okay, so along here, we have our B values. If you have S stages, you'll have S number of B values. Okay, and finally, in the top right quadrant, we have our matrix A. Now these, if I go back a slide, are what we multiply the previous values of the stages and add them onto the Y in the function evaluation. Okay, so you can see A21K1, A31K1 plus A32K2. Okay, so the C's are what we multiply H by and add them to T. The A's are what we multiply the K's by and add them to Y. Okay, so in order to actually define a Runge-Kutta method, we just need our C's, we need our B's, and we need this matrix A. And that's all we need to define a Runge-Kutta method. And that's known as a butcher tableau, after John Butcher. So he's sort of like the daddy of Runge-Kutta methods. Okay, so he thought of this way of representing them, and everyone just uses it essentially. One thing which makes, when we put it in this tableau, it makes it useful, is there is a condition that links the A and the C values. And that condition is the row sum. So if I was to sum the first row of the A's, that should give me the C. So C2 would be the sum of this, all the values on the second row of A would be the same as C2. We need that in a minute when we derive our Runge-Kutta methods. Okay. So that's a butcher tableau. Let's have a look at an example. This is sort of similar to an example which are in the tutorial exercises for this chapter. Here I have a 4-stage Runge-Kutta method. It's 4 stages, K1, K2, K3, and K4. This happens to be the 4th order Runge-Kutta method. Okay, so those are my 4 stages. Okay, and this is how I update Y. So Y n plus 1 is equal to yn plus a 6th K1 plus 2/6 K2 plus 2/6 K3 plus 1/6 K4. My B values were whatever I multiply the K's by. So first B value is a 6th, second B value is 2/6. So in other words, 1/3. The third B value is 2/6, so that's a third. And the fourth B value is 1/6. Okay, so that's also a 6th. Anybody notice anything about these values? Okay. The B values sum to 1. And that's the same with all explicit Runge-Kutta methods. So a 6th plus a third plus a third plus a 6th will sum to 1. Right, my C values, this is what we multiply H by. So here, we have nothing adding on to the T value. So C1 is 0. Here, we're adding a half H to T. so C2 is a half. Here we're adding half H again, so C3 is a half. And here we're adding a whole H, so C4 is equal to 1. So this gives me my C values. A's are what we multiply K's by. Okay. On the first stage of an explicit Runge-Kutta method, we don't add anything on to the Y values. So all of my top row of my A's are zeros. For the second stage, we're adding a half of K1 to Y. Okay. So therefore, A21 is a half. And we're not adding anything any further, anything over here. So all the other values are 0. On the third stage, we're adding nothing of K1. Okay, notice we don't have any K1s here, but we're adding a half K2. Okay, so we add no K1s and we add a half K2. Okay, and nothing else. So that those are zeros. And on the fourth stage, we just add one lots of K3. So there's no lots of K1, no lots of K2, and just one lot of K3. Okay, so that's the sort of long-handed way of writing out Runge-Kutta method. If we establish what the B, C, and A values are, we can just write that as this butcher tableau. You remember C's down the left, B's along the bottom, and A goes in the top right quadrant. Notice all the zeros in the upper triangular region are just ignored. Okay. This is because it's an explicit Runge-Kutta method. In an explicit method, A will always be lower triangular. So in other words, the main diagonal of the matrix A is 0, and the upper triangular region is also 0. So we just ignore it. We don't bother writing it down. Also in an explicit method, the first value of C is always 0, and the S value of C is always 1. Okay, so that's 1, that's 0, and we'll have some intermediate values in here. The S value will always be 1. So in this case, S is 4, so C4 is 1. And note that the C values are the sum of the rows of the A matrix. So a half equals a half equals 0 plus a half, and 1 equals 0 plus 0 plus 1. Okay. That's a butcher tableau. That's what we're going to be working with from now on. So when usually in an exam question, if I say, okay, derive this Runge-Kutta method, I'll normally say express it as a butcher tableau. So that's how I want you to express it. It's just a quicker way. It's an easier way of writing down all that. You could write down all that, but that's just quicker. It's quicker and it allows us to work with it a bit more easier, especially when we start looking at stability. Okay, when we start to look at the stability of these methods, it's easier to go from this to check stability. Okay, so that's the butcher tableau. Are there any questions about that? Is it sort of, can you sort of go from this form, find the B's, C's, and A's to go to the butcher tableau? Because that's what you'll be needed to do. Okay, and vice versa. If I give you a butcher tableau, you should be able to write out the K1, K2s, and the YN plus 1 from the butcher tableau. Okay. Okay, so what we're going to move on to now is the derivation of the second order Runge-Kutta method. Okay, so start as always with our first order ODE. When I say first order, I mean the highest derivative is the first order derivative. Remember, order can mean the order of the derivative, or it can mean accuracy. Okay, it's unfortunate we use the same word to mean two different things, but that's the English language for you. Okay, second order Taylor series expansion is this. That shouldn't be new to you. That should be fairly old hat by now. What we need to find is we need to find the second derivative of this. So we need to differentiate f of ty in order to find y double dash. Okay. We apply the chain rule to f of ty to give us this. Okay, so this is a chain rule. Okay, df dt times dt dt. plus the f dy times dy dt. Okay, notice these are partial derivatives. Okay, the dy dt, okay, this is the first derivative of this. Okay, so dy dt I could replace with y dash. Okay, so I've replaced the partial derivative of f with respect to t by subscript notation. Dt over dt is just 1. Okay, so that gives us that first term. Okay, then I've got the partial derivative of f with respect to y, which I've written it in subscript notation, and dy dt I've replaced by y dash. Well, up here, if this is the ODE I'm solving, y dash is equal to f of ty. So therefore, I replace y dash with f of ty. So that is the derivative of f of ty, first order derivative. That goes in to that position there. So y double dash can be replaced by this. Okay. So what we do now is we substitute y dash, which is f of ty, which is our ODE. And if I find the derivative of this ODE, I get this using the chain rule, and I replace that into the second order Taylor series. Okay, so instead of y dash, I've got f of ty. Instead of y double dash, I've got this thing in square brackets. Okay, last time I looked at bivariate Taylor series. Why did I do that? Well, it's used here in the derivation of the Runge-Kutta method. So just to refresh your memory, if I have a small step h in the t variable and I have another step k in the y variable, the first order bivariate Taylor series can be written as this. So what I can do is if you see here, I've got f of ty plus hf of t plus f of h times f of y ty plus f of ty. Okay, what I can do is I can replace this in here by the first order bivariate Taylor series. Okay, so k is h times f of ty in this case. Okay, so I can replace this in here, so I can write down this in using the first order bivariate Taylor series. Okay, so all I've done there is I've replaced the square bracket with the bivariate Taylor series, and that gives me that. Okay. So this is what I've got so far, and from this I can write down my scheme. Okay, if I let K1 be h of f of ty, okay, so h f of ty there, and I'm going to let K2 be this term here. Okay, h times f of t plus h plus y plus h f of ty. But if K1 is h f of ty, then I just got y plus K1. Okay. So what I've done is I'm writing down that Taylor series in 2 steps. There's my K1, there's my K2. As you can see, K1 is multiplied by 1/2 and K2 is multiplied by 1/2. So that's the Taylor series written in terms of K1 and K2. And that is the second order Runge-Kutta method. So what have I done there? To derive that method, okay, I'll just go back a couple of slides. I've taken the Taylor series. Okay, I've replaced the second derivative of y with the derivative of f of ty. Jiggled it about a bit and written it in that form. So it's essentially second order Taylor series written in that form. That's all the Runge-Kutta method is. That's how we derive them. Okay, well that's my second order Runge-Kutta method. It's easier to write that as this in the butcher tableau. So remember down the left, we have our C values. So C is 0, and then in this case, C is 1. And on the bottom, we have our B values. So this is what we multiply K1 and K2 by. And this A matrix is what we multiply K1 by here. And notice that 1 is equal to the row sum of the A matrix. Okay. That's the second order Runge-Kutta method. That's actually referred to as the classical second order Runge-Kutta method. There are an infinite number of second order Runge-Kutta methods. Okay. We refer to that one as the classical one because it tends to be the easiest. Okay, so there are, as I just mentioned, there are an infinite number. So what if we wanted to derive a different second order Runge-Kutta method? So what we've got to do now is we've got to look at it in general terms. Okay, so this is in general form of an RK2 method. First stage is always f of t, h times f of ty. Second step, if I'm writing out in general terms, we have t plus c2 times h, y plus a21 times k1. Okay, so all I've done here is I've written out the butcher tableau using general terms. Okay, so b1, b2 on the bottom. c1 is always 0. c2, well, actually, that should always be 1, but I've written it in general terms of c1 there and a2 on there. Okay. We need combinations of these values, these 4 values that satisfy the Taylor series. Okay, so we're looking for different combinations of these 4 that satisfy the Taylor series expansion. Okay, well, if I first look at the K terms, okay, bivariate Taylor series, what I've done here is I've got t plus something times h. Okay, so if I'm going to just backtrack a couple of slides, okay, there's my bivariate Taylor series. Okay, I've just got t plus h. What happens if I got t plus something times h? Okay, so I'll go forward a couple. Okay, so I've got c2 times h times the partial derivative of f with respect to t. And here I've got y plus something times k1. And that's where that something comes from. Okay, so that's just a bivariate Taylor series where we're multiplying our h and our k by c1 and a21 respectively. Okay, what I can do here is I can replace, where's my pointer gone? I can replace k1 by h f of ty. Okay, so that's always the first stage. So if I have k1 here, I can replace it by h f of ty, and that's what I've done there. So what we've got, my Taylor series, second order Taylor series, y of t plus b1, okay, times k1, which is always f of h ty, plus b2 times h plus this. Okay, so all I've done is I've replaced, that's the second derivative using the bivariate, the bivariate Taylor series. Okay, so replace this f of t plus c2h, y plus a21 k1 by this side here. Okay, and here I've done a bit of simplification. So here we've got b1 times h f of ty plus b2 times h f of ty. So I've done a bit of what's the word? Totally mind blank. Yeah, connecting terms, factorization, connecting terms. Okay, this is what I end up with. It's rather ugly, ghastly, horrible. Okay, but what I can do is compare it to the Taylor series. So this is what we got. This is that horrible. This is that horrible thing. This comes from the Taylor series with my K1 and K2 substituted into it in general terms. This is what I want to have. Okay, this is what I'm looking for. This is what I'm aiming for. This is what I've got. So in order for this to be equal to this, the B1 plus B2 should be 1. Okay, can you see B1 plus B2 is multiplied by H f of Ty. And what we want is simply 1 times H f of Ty. So the B1 plus B2 should be equal to 1. Okay, what else do I want? Well, my partial derivative of f with respect to t should be multiplied by h squared over 2. At the moment, in this one, it's being multiplied by b2 times c2 times h squared. So I need b2 multiplied by c2 to be equal to 1/2. And that's where that comes from. What else do I need? Well, my partial derivative of y, partial derivative with respect to y of f times f, I want that to be equal to h squared over 2. So I'm multiplying that by h squared over 2 down there. Well, up here, it's being multiplied by b2 times a21 times h squared. So that means b2 times h21 must also equal to 1/2. So this was using that horrible Bivariate Taylor series, all that gumph. This is what I wanted. So in order to get this, I need to satisfy these equations. This is what we call the order conditions. When I ask you in an exam to derive a Runge-Kutta method, I'm not going to ask you to do all this. Okay, is there a bit of a relief there? I'm not asking you to do that. What I'm asking you to do is solve this system. So you'll be given, at the moment, it's 3 equations and 4 unknowns. So you need one of the values of the unknowns to be specified. But let's say I was to give you a value of B1. You can therefore, you can calculate B2. Using that, you can calculate C2. And using that, you can calculate A21. So when I ask you to derive a Runge-Kutta method, it's normally solving what we call these order conditions. Okay, so let's have a look at an example. I've let C2 be a free parameter. I could have let any of the others be a free parameter. Okay, it doesn't matter. All 3 equations and 4 unknowns, I just need to specify one of them. So if C2 is a free parameter, okay, solving, we get this. So therefore, I can say the butcher tableau for a second order Runge-Kutta method is this. Okay. So that should be sort of make you feel a bit nicer. That 10 minutes of derivation, okay, I admit it's a bit horrible, but you don't need to worry about that. What you do need to realize, though, is where these order conditions come from. We just compare our Taylor series from the general Runge-Kutta method and the Bivariate Taylor series with our second order Taylor series. We're trying to get this equal to that. And in order to do so, we have to satisfy these conditions. Okay, so that's a second order Runge-Kutta method. Right, let's have a look at an example. Derive a second order Runge-Kutta method using C2 as 1/2. Okay. Well, C2, A21 must be equal to C2 because of the row sum condition. So therefore, A21 would also be equal to 1/2. B2 is 1 over 2 times C2. So that gives us 1. And B1 is 1 minus B2. So if if B2 is 1, therefore B1 must be 0. And there's a butcher tableau for that second order Runge-Kutta method. It's the same order of accuracy as the classical second order Runge-Kutta method, just written in a different way. And this is known as the midpoint rule, which you may have seen last year. Okay. I was going to show you an example using MATLAB here, but MATLAB doesn't work on this machine, so you'll have to take my word for it, but the solutions are correct. So I'm going to use this second order Runge-Kutta method to solve this initial value problem. Okay, so my f of ty is the right-hand side to this IVP here. Okay, y plus t. The range of values for t is between 0 and 1, and the initial value for y is 1. And I'm going to use h equals 0.2. And I'm going to use this method. Okay, and I think I showed you this last time. And you get this. These are solutions. So t with a step length of 0.2. Okay, so we need 5 stages or 5 steps, sorry. This is the RK2 solution And here we have the exact solution. So you can see we do have some error. So this column is simply the absolute difference between RK2 and exact. Okay, it's second order accurate. So the error, if I was to reduce the value of H by a half, the error should be reduced by a quarter. Okay, because we have a second order method. Okay, I'm just going to probably do another couple of slides, then we'll carry on this in the second lecture. Third order Runge-Kutta methods. In order to derive these, we have to take the Taylor series to third order. I don't know about you, but I really don't want to do that. Okay, it's horrible. It really is horrible. So I'll show you what we actually do in practice. Okay, so this is a general form of the third order Runge-Kutta method. Okay, we don't tend to write it in that. We tend to write it as a butcher tableau. Okay, these values of C's, B's, and A's have to satisfy the third order requirements for the Taylor series. Okay, rather than going through the Taylor series derivation again, what we can use is these. Okay, so these are these order conditions. If my values of B, C's, and A's satisfy these four equations, then I know I have a third order Runge-Kutta method. Okay, and all we do is we derive a third order Runge-Kutta method by finding values of B, C's, and A's that satisfy these. Okay, as you can see here, how many unknowns have I got? I've got B1, B2, B3, I've got A3, 2, and I've got two values of C. So I've got six. Is there six? 1, 2, 3, 4, 5, 6, 7, 8, 9. No, 8. I can't count. Sorry about that. So we have 8 unknown values. We have 4 equations. We have to fix a couple of those values in order to satisfy these 4 equations. And that's what we'll be looking at in the second lecture. Okay. If there's anything I want you to take away from this, is that to derive Runge-Kutta methods, we have to satisfy the same requirements as the Taylor series. And that means solving these. It's not that difficult. I'm not going to ask you in an exam to do all of this. Okay, hopefully that's a bit of a relief for you. Right, okay, so there is a sign-in sheet going around. If you can put your name on it, and in the second lecture later today, we'll be looking at deriving third and fourth order methods. Yeah.
I can't understand, why Runge-Kutta they did like that.